Hello everyone, my name is Zhao Yang. I will present our research on evaluating and training verifiably robust neural networks. Our goal is to certify there is no adversarial examples in the LP ball around the original input. The key of robustness verification is to compute lower and upper bounds of the output logits of a neural network. Interval-bound propagation and Chron are two typical methods to compute these bounds. They compute these bounds by making linear relaxations of the ReLU activation. However, both of them have their own problems. IBP is fast but is very loose. Chron is relatively tight but scales poorly due to its high memory cost. So our first contribution is to design a relaxed version of Chron. Instead of backpropagating to the first layer in the original Chron process, we argue that we can stop at any intermediate layer and obtain a relaxed bound. We are particularly interested in the special case where we only backpropagate one layer. This leads us to an algorithm we name linear bound propagation. Experiments demonstrate that LBP is tighter than IBP, while has better scalability than Chron. Our another focus is on train verifiably robust neural networks. Previous works found IBP bounds are differentiable with respect to neural network parameters, and thus can be incorporated to the loss function in the training phase to encourage the network to have large verified safety regions. We notice that such networks are verified by IBP after training. One natural question to ask is whether we can use the tighter method, Chron, to verify these networks. Surprisingly, previous works found Chron gives very loose bounds for IBP trained networks. Another issue we identify is that most neurons become dead in IBP trained networks. So we first studied the relationship between Chron, LBP, and IBP. We managed to prove that Chron and LBP are guaranteed to be tighter than IBP if they choose appropriate bounding lines. And they can be used to verify IBP trained networks to achieve lower verified errors. To tackle the issue where most neurons become dead, we propose a new activation function, parameterized ramp activation. It can be seen as the ReLU activation with the right part being bent flat, and the bending point is tunable. We included it to the parameters of the network and optimize over it in the training process. The intuition behind this activation is that we provide another robust region on the right part of this activation function, and it allows a neuron to become robust while preserving representation capability. We conduct experiments to compare parameterized ramp activation with ReLU activation. Indeed, we found there is a considerable amount of neurons that are in the right dead status in an parameterized ramp network. We also find networks with parameter ramp activation function achieve lower verified errors than ReLU networks. In conclusion, we propose a relaxed version of Chron named LBP. It has better scalability than Chron while being tighter than IBP. We also prove that Chron and LBP can be used to verify IBP trained networks and obtain lower verified errors if they choose appropriate bounding lines. We also obtain an intuition on how to train verifiably robust networks. That is, we should encourage most activation values to lie within the robust regions of the activation function while preserving the representation capability of the network. Thanks for your attention.